All right, today we are diving into one of the most important ideas in all of chemistry, pH. You've definitely heard of it, but what is it really? Well, it turns out it's this invisible force that's shaping basically everything, from our own bodies to the health of the entire planet. So let's start with a bit of a riddle. What could possibly connect your stomach, a rainstorm, and the battery in your car? It sounds random, I know, but the answer is this amazing, hidden chemical balancing act that's happening all the time, right at the molecular level. And that balancing act is exactly where we need to start. To really get a handle on pH, we first have to peek inside any solution that's based in water and meet the two key players that are always at work.
See, here's the thing. Even the purest water you can find isn't just a bunch of H2O molecules hanging out. At any given moment, a tiny fraction of them are actually breaking apart and then reforming, creating these two super important charged particles: hydronium ions, which give things their acidic kick, and hydroxide ions, which make them basic.
The best way to picture this is like a chemical seesaw. In any water-based solution, these two ions are in this constant dance. If you have a whole lot of hydronium, the other side of the seesaw goes up, meaning you have to have very little hydroxide. That's an acidic solution. But if hydroxide is the dominant one, then it's basic. And what happens if they're perfectly balanced? Well, that's when a solution is neutral, just like pure water.
So that's great, right? We can measure how much of each ion there is. But for the chemists who first figured this out, there was a huge problem. The numbers they were dealing with were an absolute nightmare.
I mean, just look at that number. That's how many hydronium ions are in pure water. And other stuff, it could have concentrations millions of times bigger or smaller. Trying to compare numbers with that many zeros isn't just annoying, it's basically impossible to work with. They really needed a better system. And luckily, there was one. Chemists came up with this brilliant little mathematical trick called the p function. Now, it sounds complicated, it's just taking the negative base 10 logarithm of a number, but its job is so beautifully simple. It just tames those ridiculously messy numbers and turns them into clean, friendly ones we can actually use.
And here's the aha moment. When you take that p function and apply it to that super awkward concentration number for pure water, boom, you get a simple, elegant number, 7. That's where the pH scale comes from. It isn't random at all. It's just a direct translation of that messy concentration into something much easier to handle. Now, if you remember one thing, make it this. The pH scale is logarithmic. It works just like the Richter scale for earthquakes. A solution with a pH of 3 isn't just a little more acidic than one with a pH of 4. It is 10 times more acidic, which means something with a pH of 2 is 100 times more acidic than a pH of 4. It's an incredibly powerful way to squeeze a huge range of values onto one simple scale. Okay, enough of the theory, right? Let's bring this back down to earth. How does this abstract math actually apply to stuff we run into in our daily lives? Let's take a look.
This is where it all clicks. So if we look at the scale, way down at the super acidic end, near 0, you've got crazy strong stuff like battery acid. Then, right in the middle at 7, that's our perfectly neutral pure water. And as we move up the scale, things get more and more basic or alkaline. We pass things like baking soda and soap, all the way up to something like drain cleaner, which is incredibly basic, near the top at 14.
It's one thing to see these things on a chart, but you might be wondering, how do scientists actually figure out that specific number? How about we try it with something like stomach acid? It's actually way easier than you'd think. First, you just need to know the hydronium concentration. For stomach acid, that's about 1.2 times 10 to the negative 3. Step 2, you just plug that number into our trusty p function formula. And what do you get? A pH of 2.92. It's really as simple as that. So let's just boil it down to the simple rules of the road. Is the pH less than 7? It's acidic. Is it exactly 7? It's neutral. And if it's greater than 7, you got it. It's basic. That's the whole framework right there. Now, it's really easy to think of pH as just some number you measure in a chemistry lab, but its impact goes so far beyond that. This simple little scale helps us understand and even solve some major global challenges. Let's talk about rainwater, for instance. You might be surprised to learn that even perfectly clean rain is naturally a little bit acidic. That's just because carbon dioxide in the air dissolves into it. But when that pH drops below 5, we have a problem. We call it acid rain, and that's when things get serious. So what's causing this dangerous drop? Well, it's all about pollutants. Sure, some come from natural things like volcanoes, but the biggest culprits by far are sulfur and nitrogen oxides that come from us, from burning fossil fuels in our cars, in power plants, and from big industrial factories. When those gases get into the atmosphere, they mix with water and form some pretty powerful acids.
And the damage this stuff does is no joke. Acid rain can literally eat away at marble statues and the fronts of old buildings. For decades, especially in places like North America and Europe, it completely wrecked entire ecosystems. It wiped out forests and made lakes so acidic that fish and other life just couldn't survive anymore. That is the devastating power of just a 1 or 2 point shift on the pH scale.
But it's not just out there. The stakes are just as high right inside our own bodies. Our blood has to be kept in this incredibly tight pH window, right around 7.3. If it strays even a little bit from that, the enzymes that run all the chemical reactions in our cells can just stop working. It's a perfect example of how a delicate pH balance is absolutely critical for life itself.
So, from the acid in our stomachs to the rain falling from the sky, pH is this amazing tool that lets us see and measure an invisible chemical reality. It gives us a number for it. And that kind of leaves you with a pretty big question, doesn't it? What other crucial invisible forces are out there shaping our world, just waiting for us to find the right scale to bring them into the light?